Hello everyone, my name is Tasneem Safdari and in today's video I am going to explain question number 7 of NSEM paper. In the previous videos I have explained till question number 6 both part A and B, and in today's video I am going to explain question number 7. So let's start. Part A of the question number says, explain k-means clustering algorithm with steps. Discuss how initial centroids influence result. So, what is k-mean clustering? So, is an unsupervised machine learning algorithm used to group data into k clusters based on similarity. So, each cluster is represented by its centroid. There is a means center value which is known as centroid. So every cluster is represented by it. So what is the goal of k means? To divide data group in k groups so that points inside the clusters are similar and points from different clusters are different. Each cluster has a center point which is the centroid. So how does k means work? So we'll choose k, decide how many clusters you want. So example 2, 3, 4, this many clusters we can have. So for example we choose k equal to 3, that is we want 3 clusters. Now we'll select the initial centroid. So pick k random points from the data sets as starting centroids. Example, choose 3 points randomly. Since we have chose the value of k as 3, so we need 3 centroids for each cluster. So randomly we'll choose 3 points C1, C2 and C3. Assign points to nearest centroids. For every data point, compute distance from each centroid. So we'll compute the distance of the point from the centroid, which is usually the Euclidean distance, and assign the point to the cluster whose centroid is closest. This forms temporary cluster. Once all points are assigned, for each cluster compute the mean or average of all points, and this new mean becomes the new centroid. So centroids will move. Reassign points. Using the new centroids, again assign every point to nearest centroid. Now we'll again assign every point to the nearest centroid and form the updated clusters. We'll repeat steps 4 and 5. Continue recalculating cluster and reassigning points until cluster assignments stop changing or centroids stop moving or maximum iterations are reached. So this is called convergence. So this is the stopping point of assigning the centroids. Now, when the algorithm stabilizes, the cluster formed are the final k clusters, and the final centroids of each group represents that cluster. So, what is the summary? We'll choose k and we'll pick k initial random centroids and assign each data points to the nearest centroids, and we'll compute new centroids from the formed cluster. Reassign points. Repeat until centroids stop changing. So how initial centroids influence results? So this is the most important concept. Different initial centroids means different clusters, because k means random starts from random centroids. The final cluster can be different each time you run the algorithm. Risk of converging to a local optimum. K means tries to minimize within cluster distance, but if starting centroids are bad, the algorithm may end in a poor quality clustering. So it may not find the best solution, only a local best. Slow convergence if centroids start far. If initial centroids are poorly chosen, so algorithm may take more iteration, takes longer to stabilize. Okay, it might take longer to stabilize. Can produce uneven clusters. Bad initial centroids may lead to one cluster having many points, another cluster having very few distorted boundaries. So it will form uneven clusters. This reduces clustering quality. Example of influence. The dataset has two natural groups. Good initial centroids. Two starting points land in separate groups. Algorithm finds correct cluster easily. Paired initial centroids, both starting point fall inside the same natural group. K-means may split one group unnecessarily and mix points incorrectly. How to reduce the problem? To avoid best result, use k-mean plus initialization. Select first centroid randomly. Other centroids are chosen far apart. This gives best, more stable clusters. And run k-means multiple times. Pick the best results based on lower error, which is inertia. So k-means is simpler clustering algorithms that works by repeatedly assigning points to nearest centroids and then updating centroids based on cluster means. However, the choice of initial centroids affects the final clusters because the algorithm may converge to different solutions depending on where it starts. Poorly chosen centroids may lead to slow convergence, incorrect cluster shapes, or poor clustering quality. Using techniques like k-mean helps improve the reliability of the result. So this was part A of question number 7, where we have understand what is k-mean clustering, how the initial centroids influence our result. Now let's move to part B. So completely demonstrate the clustering algorithm and a KNN classification example using Euclidean distance. So what is K nearest neighbor? So K is a lazy instance based supervised learning method. For classification, it assigns the class most common among the k nearest training example to the query point. For regression, it predicts the average of the k nearest target values. It does no training. It stores the training data and performs computation at prediction time. That's why it is called lazy training. So when to use KN? Small to medium data sets, problems where the decision boundary is non-linear and you prefer a simpler method. Good baseline for classification and regression. Works well when similar inputs have similar outputs, which is locality assumptions. So algorithm step by step. Choose K, number of neighbors, and select a distance metric. Usually we do with Euclidean. And for each query point, compute the distance from the query to every point in the training set. Sort training points by distance, which is in ascending order, small to big, and select the top k nearest neighbors. Vote for classification. Count the classes amongst neighbors. Choose the majority class. For ties, use tie breaking rule. Smaller k, choose the class of or use class priors. Optionally weight neighbors. Return predicted class or regression value. So distance matrix, it is a common choice. We have Euclidean L2. Formula for the same is given on the screen. Default for continuous features. Then Manhattan-Minkowski cosine similarity, which is 1 minus p into q upon mod of p into mod of q, and Hamming for categorical or binary features. So these are distance matrix, which are common choices. The Euclidean is used for default for continuous features. Then Manhattan-Minkowski general form is p parameter, cosine similarity, Hamming. Now choice of k, small k, example 1, low bias, high variance, sensitive to noise and outliers. Large k, higher bias, low variance. Typical practice, try odd k for binary classification. Use cross validation to pick k. Will choose k. If k is small, it means low bias, high variance, and larger k, higher bias, low variance. Typical practice, try odd k for binary classification. Then weighting neighbors, uniform weights, each neighbor votes equally. Distance weighting weights or Gauss weighting reduce the effects of farther neighbors. Now pre-processing and practical consideration. Feature scaling is essential for distance-based methods. Without scaling, features with large ranges dominate distances. Handle categorical features by using appropriate encoding and possibly different distance metrics. Missing values. Impute or use distances that ignore missing dimensions. Imbalanced classes. KNN can be biased towards majority class. Use stratified sampling class weights or smaller k. Curse of dimensionality. In high dimensions, distances becomes less meaningful. Consider dimensionality reduction like PCA, feature selection, or using appropriate distance. Then computational cost. Naive KNN is O of n per query. Use acceleration structures, KD tree, ball tree, or approximate methods, LSH, NOI, phase, or for larger data set. Now complexity. Training time O of 1, only storing data. Prediction time O of n into d per query. N is train examples and d is features. And memory O of n into d. Evaluation metrics for classification: accuracy, precision, recall, F1, ROC, AUC. Choose based on class. We have seen we use confusion matrix to calculate accuracy, precision, recall, F1 score. So use cross validation to estimate generalization performance and to pick K. KNN in text mining and sparse data. Represent documents by TF IDF vectors. Cosine similarity is common because magnitudes vary. It measures orientation instead of length. For TF IDF, you must normalize vectors, that is in L2 normalization, before computing cosine. Ties and tie breaking. There is a tie in votes. Common rules. So choose class of nearest neighbor among tied groups. Reduce K or randomly break tie consistently. Use distance weighted voting to avoid ties. Improvements and variants. KD trees or ball trees for fastest nearest neighbor search, and approximate nearest neighbor for very large high dimensional data. Use metric learning to improve performance. Use prototype reduction to reduce memory. Now worked numerical example, Euclidean classification. Like we have a training set in which we have point A, B, C, D, X is 1, 2, 3, 6 and Y is this, and class is red, red, blue, blue. So query point Q 3, 2 and we have chose K equal to 3. So using Euclidean distance, which is square root of xq minus x square plus yq minus y square. So compute each distance digit by digit. So first our point is A is 1, Q is A 1, 2. So x difference 3 minus 1 is 2. There is a problem in document. So 3 minus 1 is 2 and 2 minus 2 is 0. And square differences. 2 to the power 2 is 4 and 0 to the power 2 is 0. And sum squares 4 plus 0 equal to 4. And when we find the square root of 4, it is 2.00. So D distance DQ, A is 2.0. Similarly for B 2, 3, 3 minus 2 is 1, 2 minus 3 is 1. And we'll find the squares, that is 1 to the power 2 is 1 and minus 1 to the power 2 is also 1. So 1 plus 1 is 2 and square root of 2 is approximately 1.41. Round to 3 decimal places, 1.414. So this is the distance. Now we have a C point 3, 3. So difference will be 3 minus 3 is equal to 0 and 2 minus 3 is equal to minus 1. So squares will be 0 and 1 and sum will be 1 and square root of 1 is 1. So this is for Q, C. And for D 6, 5, we'll find the difference. 3 minus 6 is minus 3 and 2 minus 5 is minus 3. Squares will be 9 for both 9, and sum will be 9 plus 9 18, and when we find the square root of 18 we get answer as 4.242, and rounding off to 6 and rounding off to 3 decimal places 4.243. so we have a distance CBAD. We have arranged it, sorted it in the ascending orders. So we got this list. So K equal to 3, nearest neighbor CBA, blue, red, red. Majority votes, red equal to 2, blue equal to 1. So prediction is red. If we use distance weight should be, that is 1 by D. So weight should be this. And the sum of weights, all of their sum is, for red is 1.207 and for blue is 1.00. So still red wins. So practical recipe, how to apply KNN well. So pre-process, handle missing values, encode categorical variables using one-hot encoding, and scale features. Choose metric, Euclidean for continuous numeric features, cosine for text or sparse data. Select K. Use cross validation. Try several odd K values like 1, 3, 5, 7, 9. Plot validation errors versus K and choose K with lowest validation error or where curve flattens. Consider weighing. If nearer neighbor should matter more, use distance weighting. Acceleration for large N, use KD tree, ball tree or approximate nearest neighbor libraries. Evaluate. Use cross validation confusion matrix to precision recall F1. Advantages and disadvantages. Advantages, it is very simple and intuitive. No training time, fast to set up, naturally handles multi-class problems, non-parametric, and can model complex decision boundaries. Disadvantages, prediction can be slow for larger data sets, memory intensive, performance degrades in high dimensions, sensitive to irrelevant or differently scaled features and to noisy data outliers. So these are the advantages and disadvantages. Now there is an extra tip. Use dimensionality reduction PCA if features are many. For text, use TF or IDF plus cosine and K, usually in range 5 to 15 depending on data. For imbalanced data sets, consider using different K or weighing or combine with resampling methods. So this was all about question number 7, both part A and B. We have discussed both parts in very much detail. We'll be discussing the next remaining questions in the next videos. I hope you liked it. Thank you so much for watching.